Good evening, everyone. We'll be starting with the second lecture of semiconductor devices, right? In the last lecture, we discussed about different types of conductors, semiconductors, right? We discussed about the extrinsic semiconductor. We discussed about the intrinsic semiconductor, right? Intrinsic semiconductor was a semiconductor of its purest form, and extrinsic semiconductor was the impure semiconductor, right, where we do the doping of some elements or some dopants, right, to increase the conductivity of a semiconductor devices. Because the conductivity of intrinsic semiconductor is less, very less at room temperature as compared to the conductivity of extrinsic semiconductors, right? So now we have different types of semiconductors, P-type semiconductor, N-type semiconductor, right? Now, the combination of these semiconductors lead to the formation of the PN junction, right? That's the P-type, N-type semiconductor, right? And when P-type semiconductor is joined to N-type semiconductor, such type of crystal, right, is called as the PN junction diode, right? And it leads to the formation of a diode, right? Now, in PN junction diode, there are two types of currents, right? One is the current due to the majority carriers. We know that in P type, the holes are in excess, and in N type semiconductors, the negative charge of the electrons are in excess, right? So the when two diodes are actually connected or joined to each other, there is a concentration gradient, or right? We can say that there is a concentration gradient between the hole and the uh, hole and the electrons, right? So because of that concentration gradient, there is a current what we call as the diffusion current, right? And we can say that diffusion current occurs because of the majority carriers, right? For P-type, the majority carriers are hole, and for N-type, the electrons are the majority carriers, right? And this leads to the diffusion current. Diffusion current. When we join the P-type and N-type semiconductor, right? Diffusion occurs from the P-type to the N-type, right? So there is a what we call as flow of holes from the p-type and flow of electrons from the n side of the junction. This leads to the formation of the diffusion current, right? And the direction of this diffusion current is from p side to n side of semiconductor, right? Now, apart from majority carriers in p-type, there is also minority carriers, minority charge carriers, which are electrons in case of p-type, and which are there are holes in case of n-type semiconductors, right? And because of the current, because of these minority carriers, right? This current we call as drift current, right? Drift current. And once the diffusion current is established, right, then the N side attains the positive charge and the P side attains the negative charge, right? Because of the deficiency of the electrons, because of the flow of the diffusion current, N type attains positive charge and the P type attains the negative charge, right? There's a concentration barrier, or we can say there is a electric field set up in a region, right? In a region where the two junctions are actually connected to each other, and that region we call as depletion region, right? So once the depletion region is established, right, now the current because of the majority carrier stops. Now the current is only because of the minority carriers of P type and the minority carriers of N type. That current we call as drift current, right? So drift current is because of the minority carriers, and diffusion current is because of the majority carriers of P-type and N-type, right? Now you can see this is the P-type semiconductor, right? This is the P-type semiconductor, and this is the N-type semiconductor here, right? Now once the majority carriers flow from P-type, right, or we can say holes flow from P to this junction point, right? And electrons flow from this n side to this junction point. This side of the n type becomes positively charged, and this side becomes, or we can say it becomes hole deficient, right? That's the reason we give it a negative charge right here. So this becomes at comes at lower potential, right? Or we can say negative. It becomes a negative side, right? And n side becomes at the comes at the higher potential, right? So this region we call as depletion region, right? This is the region where actually the barrier of the electric field is set. This region we call as depletion region. This is the depletion region, right? This is the depletion region, right? Direction of the diffusion current is from P to N, but the direction of drift current is from N to P, right? It's opposite to that of the diffusion current, right? Initially, diffusion current is large and drift current is small. As the process continues, there is an electric field set up in the depletion region, right? Which stops, which stops the which stops the diffusion current, and which in turn increases the flow of the drift current, right? This process continues until there is no current flowing, or we can say the diffusion current becomes equal to the drift current, right? And now, once this process stops, right? Now the current stops because the current due to the majority carriers becomes equal to the current due to the minority carriers, and this equilibrium at equilibrium stage in PN junction, right? There is no current, and we say a junction is formed. That's what we call as the p-n junction diode, right? So electric field setup is set up from N side to P side, right? P side is at higher potential. You can see the P side is at higher potential, right? And N side is at higher potential, and P side is at lower potential, right? Now the difference in the potential, right? Or we can say the electric field is set, right? Difference in the potential between the N side and P side, this potential stops the flow of the current because of the majority carriers, right? And this potential we call as barrier potential, right? This acts as a barrier, and hence it's called as the barrier potential for the PN junction diode, right? So every PN junction diode, when it's not biased, right? Or we can say it's not connected to any battery, right? There's a region what we call as depletion region, and in that depletion region there's electric field set, or we can say there's a barrier potential which stops the flow of the current because of the majority carriers, right? Now, in order to increase the current because of the majority carriers, what we have to do, we have to do the biasing of this semiconductor device, right? So as to allow the flow of current because of the majority carriers from P type and the majority carriers from the N type, right? So the electric, or we can say the symbol of P type PN junction diode is this is the symbol of PN junction diode, right? This is the symbol of PN junction diode. This represents P side of the diode, and this represents the N side of a diode, right? So this is the symbol of p-n junction diode. You can see here. This is the P side and this is the N side, and this is nothing. This is the here the recombination of the holes and the electron takes place, right? This is what we call as depletion region, right? This is the depletion region. Now, in order to decrease this potential barrier, right, between the P type and the N type, what we have to do is we have to apply the external biasing to this PN junction diode, right? Now we do two types of biasing for this diode. One is the forward biasing, another is the reverse biasing, right? Now let's suppose if we connect the P side of the junction with the higher potential of the battery, right, and N side with the lower potential of the battery, then such type of biasing we call as forward biasing, right? We call as forward biasing, and the direction of the applied voltage is opposite to the direction of the barrier potential, right? Once the P type, or we can say P injection diode, is forward biased, then the potential barrier decreases continuously as we increase the biasing of this P injection diode till the height of this barrier is effectively reduced to zero, right? So in that case, if we at least apply the potential, if we at least connect a biasing at least equal to the barrier potential, that in that case, the net potential or net biasing between the at the junction of this diode will be equal to zero, or we can say the external biasing will become equal to the barrier potential, right? And once if we slightly increase this external potential more than this barrier potential, then it will be completely a forward bias type, or we can say there will be a complete flow of current because of the majority carriers from P type to N type, or we can say that PN junction diode will be in on state, or it will be conducting the current, right? It will be in on state, right? Now you can see here. This is the circuit diagram for the forward biasing, right? This is the circuit diagram for the forward biasing. We are connecting, there's a voltmeter parallel to this P injection diode and ammeter, right? And there is a variable potential that we supply to this P injection diode, right? Once we change the potential of this P injection diode, the current initially becomes zero until the barrier potential is removed, right? Until the barrier potential is removed, right? So there is a small current, there's still a small current, and that current is because of the minority carries, or we can say that current is because of the drift current, right? Now, once we continuously increase the biasing, right, the current slowly and steadily increases, right? And at some point, let's suppose this is a silicon diode, right? It's the silicon diode. The barrier potential of silicon diode is barrier potential for the silicon diode is 0.7 volt, right? This is the barrier potential for the silicon diode. So once this barrier potential or the external biasing or the forward voltage becomes equal to this barrier voltage, right? Then suddenly there is an increase in the forward current, right? In this PN junction, right? And this minimum voltage supplied to the PN junction, right, or forward voltage, so that the current increases exponentially here, right? And this voltage we call here as knee voltage, right? So this is nothing. This is what we call as the knee voltage, right? This is nothing. We call it as knee voltage. So at knee voltage, right, there is some sufficient forward current flowing through this P injection, right? And suddenly this current increases exponentially, right? And this minimum voltage we call as knee voltage for this P injection, right? Now, this is the current flowing. This is the nature of the current. This is how the current actually flows, right? When the PN junction diode is forward biased, right? When PN junction diode is forward biased. Now, what will happen if we further reverse bias the PN junction diode, right? So if we reverse bias the PN junction diode, it means that we'll connect the negative end of the battery to the P type of this diode and P side of this diode, and we'll connect the positive end of this battery with the N side of this diode, right? Because of that, the barrier potential is now going to increase again, right? The barrier potential will not decrease, the barrier potential will increase. When the barrier potential increases, the electric field set in the depletion region will actually increase, because the potential difference between the N side and the P side will increase because of the reverse biasing, right? Now, what will happen because of the reverse biasing? The current will increase because of the minority carriers, right? Because of the minority carriers. There will be no current because of the majority carriers, right? So the effective potential barrier height under forward biasing will be, if V is the forward biasing and V naught is the barrier potential, then the effective barrier height under reverse biasing, right? Not forward biasing, no reverse biasing. It will be V naught plus V, right? That will be under reverse biasing. Now you can see here, this is the characteristic circuit of reverse biasing, right, of p injection diode. So reverse bias region, what happens? The reverse current increases because of the increase in the reverse current, right? We can say reverse biasing, right? The reverse current increases. Then at some point, because of the increase of the reverse current, there occurs a breakdown, right? There occurs a breakdown, right? Or we can say these reverse carriers, or we can say minority carriers, further breaks the bonds, right? Because of the breakage of the bonds, the density or the number density of the minority carriers actually increases, and because of that increase in the current, the reverse current actually increases exponentially then, right? That region we call as reverse breakdown region. So what happens in the reverse breakdown voltage or reverse breakdown region? At this region, when the reverse current increases, they further break the bonds of a semiconductor material, right? Because of that breaking of the bonds, the number of minority carriers increase, right? Upon increasing the minority carriers, the reverse current increases exponentially, right? It increases exponentially, and that voltage where breakdown occurs in the reverse biasing, we call that as reverse breakdown voltage, right? For the P injection diode, right? So this is how we can bias the P injection diode, right? In the reverse bias condition, right? We'll connect the negative potential, negative end of the battery with the P type and the positive end of the battery with the N type, right? So this is the symbol of a P injection diode, right? This is the P injection diode, and this is the reverse forward biased P injection diode, right? And this is the reverse biased P injection diode, right? So for forward biased, it will be P will be always at higher potential and N will be at lower potential, and for reverse bias, P will be at lower potential and N will be at higher potential, right? Now, combining both the graphs for the forward biased and the reverse biasing. So this is how this will be for the forward biasing and this will be for the reverse biasing, right? Now, this is the voltage we call as reverse biased, reverse breakdown voltage, right? At this voltage, the current because of the minority carriers increases exponentially because of the breaking of the bonds, right, within the material, right? And this current we call as reverse saturation current, right? And here this voltage we call as knee voltage. At this voltage the forward current actually increases exponentially, right? This voltage is actually equal to the barrier potential, right? So if we supply or if we apply the forward bias equal to the knee voltage, then at this point the forward current will increase exponentially or the barrier potential will be removed from the junction completely, right? Now let's try to solve questions based on p junction diode, right? In this figure, we have been given a diode connected to an external resistance, right? There is a diode connected to an external resistance, right? And an EMF assuming that the barrier potential developed in diode, right, is 0.5 volt, right? It's assumed that or it's given that the barrier potential in this diode is 0.5 volt. Obtain the value of current in the circuit, right, in milliampere, right? Now, there is a total supply of 4.5 volts by the battery, right? Uh, point volt will be point 0.5 volt will be utilized in breaking the barrier potential of this diode, right? Then only there will be current because of the majority carries in this circuit, or we can say the current will be detected, right? So there will be a potential, we can say, equal to 0.5 volts, right, across this diode, right? Now let's talk about the circuit diagram of the p injection diode, right? Now when diode is assumed to be an ideal diode, right? When a diode is assumed to be an ideal, right, or we can say that there is no resistance across the diode, right? Or we can say if there is no barrier potential given in this diode, what we can do is that we can just replace in the forward biasing condition diode with short line, right? We can just replace this diode with the short line if the internal resistance of diode is equal to zero, right? In the ideal situation, right? We can equivalently write it like this in the ideal situation, right? So this is in the ideal situation, right? Or if there is a barrier potential given in this diode, right? There is some barrier potential, right? We can ideally represent this diode as with the battery, right? With the battery, right? This will be the higher potential, this will be in lower potential, and this will be called as the barrier potential, right? This is how we can replace the diode with this battery, right? Where the potential difference across this battery will be the barrier potential of this diode, right? So this P type, this is N type, right? This is P and this is N. If the resistance of the diode is also given, right? This is the practical situation or non-ideal situation, right? Then in that case, we have to apply the forward resistance of this diode, right? And then the barrier potential, right? This is in the what we call as the ideal situation. But this situation is only applicable when the diode is forward biased, right? It should be forward biased, right? The diode is forward biased. This is in case of forward biasing. And in reverse biasing, right? In reverse biasing, so we can say ideally it will be replaced by a short circuit, right? It will be replaced by a connecting wire in an ideal situation where we assume that the barrier potential of this diode is zero, right? Or if the barrier potential of this diode is given, we'll just replace the barrier potential with the battery of the voltage equal to the barrier potential, right? But if the resistance of the diode is also given, that's the practical situation, then we will replace this diode with the forward resistance and the battery, right? Now, in the reverse bias condition, there will be no current flowing through this diode, right? We can replace this diode with an open circuit, right? We'll just open this diode or remove this diode from the circuit in the reverse bias condition. Now, here we can see the diode is in the forward biasing condition. There will be 0.5 volt across this, right, across these two ends of this diode, right, 0.5 volt, right, and 4 volt will be across this what we call as 100 ohm resistor, right, and then current I will be flowing through the circuit, and the current I flowing through the circuit will be 4 upon 100, right, it will be 4 upon 100, right. So this much of amperes, or we can write it as it will be equal to 1 upon 25, right, amperes. So this much of current will be flowing through the circuit in the power bias condition, right, in this P-N junction diode. Now, if current in given circuit is 0.1 ampere, then calculate the resistance of P-N junction, right? Resistance of P-N junction, right? Since there is no barrier potential given in this diode, right? We will assume that the barrier potential of this diode is actually zero, right? But there is a resistance offered by this diode, right? Let's suppose we'll replace the resistance of this diode with RF, right? RF, and there will be the this resistor, right? And the battery will be of 5 volts, and there is 10 ohm resistor as well, right? 10 ohm resistor as well. This is a 5 volt battery, right? And the total current here will be equal to the total potential supplied by this battery, that's 5 volts, upon the total resistance, that is 40 plus RF, right? Now we have to find this forward resistance of this P-N junction diode, right? The current is given as 0.1 ampere, right? We'll just uh, put I equal to 0.1, right? So if the value of I is 0.1, so 40 plus RF will be nothing. That will be equal to 5 upon zero point 0.1, right? That will be equal to 50, right? That will be equal to 50. Or the forward resistance offered by this diode will be 50 minus 40. That's equal to 10 ohms, right? That's equal to 10 ohms. So 10 ohm resistance will be offered by this PN diode, right? In the forward biasing condition, right? Now, let's discuss this circuit as well, right? There are two circuits, right? There's a diode in the circuit, right? You can see there's a diode in the circuit in this fashion, right? There's a diode in the circuit in the given fashion. This is the diode here. The question is that what is the value of current I in given circuit, right? What is the value of current I in given circuit? Now we can see that this is the higher potential of the battery, or the positive end of the battery. This is the negative end of the battery, right? It means that this since the current is flowing from the higher potential to the lower potential, right, of the battery, right? That means that this end this end of this diode will be at higher potential, right? This end of this diode will be at higher potential. So this will be at higher potential, right? And the P end will be at lower potential, right? It will be at lower potential, right? It will be at lower potential. So it means that here the P junction diode is in reverse biasing condition, right? Reverse biasing condition means off state, right? Reverse biasing condition, right? Or we can say the P junction diode is in off state, right? It's not in on state, it's in off state, right? It's in off state. So when P junction diode is in off state, we can just replace the P junction diode with the open circuit, right? It can be replaced by the open circuit, or we can just directly remove this uh, diode from the circuit, right? So there will be no effect because of this diode, right? When we remove this diode from the circuit, we'll be left with 10 ohm resistor and 10 ohm resistor. Therefore, the current through the circuit will be I, that will be equal to 10, and that will be equal to 20 upon 10 plus 10, right? That will be equal to 20 upon 20. That's equal to 1 ampere, right? So 1 ampere current will be flowing through this circuit because the PN junction diode is in reverse biased condition, right? Now, let's look at this another question, right? Now in this question, you can see we have two diodes here, right? One is silicon diode, another is the germanium diode, right? The barrier potential for both the diodes is given. For the silicon, the barrier potential is 0.7 volt, and for germanium, it's 0.3 volt, right? Now there is some current flowing through this circuit. We have to calculate the value of this current, right? Now you can see here. There are. This is how the silicon diode is connected, and this is how the germanium diode is connected, right? Now you can see here, the positive end of this battery is actually connected for the P type of the silicon diode, right? And the positive end is connected for the N type of this germanium diode, right? Or we can say this diode will be reverse biased or off state, right? This will be in the off state, right? And this diode will be in forward biased, and or we can say this will be in on state, right? This will be in on state. So silicon is in on state and the germanium is in off state, right? Or if germanium is in off state, so it means that there will be no current flowing through this diode, right, at all, right? This diode will be in the off state, right? We can just remove this diode from the circuit. We'll be left with silicon diode only, right? It means the current I will flow through the silicon diode only. There will be no current through the germanium diode, right? There will be no current through the germanium diode, right? And 2.7 volt is the potential supplied by the battery, and apart from 2.7 volt, zero point 0.7 volt will be consumed or utilized in the barrier potential of the silicon diode, right? So rest of the potential will be across this 1 kilo ohm resistor, right? So the current through the circuit will be the remaining potential is 2 volts, right? That will be equal to 2 upon 1 kilo ohm, right? 1 kilo ohm, right? 2 upon 1 kilo ohm. So that will be equal to 2 milliamperes, right? The current through the circuit is nothing that's equal to the 2 milliamperes, right? 2 milliamperes will be the current through the circuit. Now let's talk about the what we call as half wave rectifier, right? This half wave rectifier also works in the on the same conditions, right? When the PN junction diode will be forward biased or when it will be reverse biased. So actually the rectifier is used to convert an AC into DC current, right? Or we can say it is used to convert AC into a pulsating DC, right? So you can see there are two types of rectifiers. One is half wave rectifier, another is a full wave rectifier, right? In the half wave rectifier, there are two circuits. One is the primary circuit, another is the secondary circuit, right? We supply an AC voltage to this circuit, right? To the, using some source, right? Using some primary source, right? To this, and we feed this AC voltage to this circuit, right? Which is connected where the diode is connected in the circuit, and there is some resistance that we call as the load resistor, right? RL, right? This is the external resistor, right? Now, what happens? How we can actually convert the supplied AC into a pulsating DC, right? We know that the AC current is sinusoidal in nature, or we can say that the AC voltage is sinusoidal in nature, right? So if this AC is supplied to this circuit, right, this is the input voltage. We can say this is P input, right? This is V input supplied to this circuit. This is the positive half of the cycle. This is the negative half of the cycle, right? You can see here's a diode. This is the diode connected, right? For the positive half of the cycle, the P type will become positive, right? P type will become positive and N type will become negative, or we can say this diode will connect, right? This diode will conduct actually, right? This diode will conduct. So ideally speaking, whatever be the voltage, input voltage given to the circuit, same will be the output voltage, right? Same will be the output voltage or output supply in the forward biasing condition, right? Or we can say positive half cycle, right? In the positive half cycle, the half wave rectifier is in the forward biasing condition. So for the positive half cycle, the output will be equal to input, right? So it means it will conduct, right? So this will be the for positive half cycle, right? But talking about the negative half cycle, right? Talking about the negative half cycle, in the negative half cycle, you can see here in the negative half cycle, the P type will become at negative potential and the N type will become at the positive potential, or we can say the diode will be in the off state, right? The diode will be in the off state, right? In the forward condition, the diode will be in on state or it will conduct, right? But in the reverse biasing condition, it will be in off state, right? So there is on state for this diode, there is off state for this diode, right? Or we can say for the negative half cycle, this will not conduct, or we can say for the negative half cycle from here to here, right? From here to here, there will be no current at all, right? There will be no current at all. Or we can say there will be no output at all, right? If there is no output at all, then once again, uh, there will be a positive half cycle, right? Now again, it will conduct for the positive half cycle, right? It will conduct for the positive half cycle, right? It will conduct for the positive half cycle. and for once again it will not conduct for the negative half cycle, right? So how this is how the output will be for the half wave rectifier, right? Right. So for the negative half cycle, this will not conduct, right? Or we can say that will be in the reverse bias condition. So this is the condition, right? This is the output, right? So we can say for half of the cycle it conducts, and for rest of the cycle it does not conduct, but there is no output or output is zero, right? So this is how you can see how actually the half wave rectifier works, right? This is not an AC, right? We can say it's a pulsating DC, right? It's a pulsating DC current or pulsating DC voltage, pulsating DC output, pulsating DC output. Now talking about the frequency, let's suppose the frequency of this input voltage is F hertz, right? You can see here the cycle is completed for the output voltage for the same time, right? For the same time. So after the same time, if F is the frequency or this the T is the time period, then T is also the time period for the output in case of half wave rectifier. Or we can say input frequency is equal to output frequency in case of half wave rectifier, right? Input frequency is equal to output frequency in case of half wave rectifier for half wave rectifier, right? So for half wave rectifier, the input frequency is always equal to output frequency, right? So it conducts only for the positive cycle and it does not conduct for the negative cycle, right? Now talking about the full wave rectifier, in full wave rectifier, what we do is that we connect two diodes in the circuit, right? There are two diodes. You can see this D1 diode, right? There's D2 diode in this circuit now. Let's suppose we supply the same input voltage, right, to this circuit, right? We supply the same input voltage, same AC voltage or sinusoidal voltage to the circuit, right? That's like this. This is the same supply, right? Now what we can do is that we can plot the output voltage on the same curve, right? Now you can see here, this is the input, right? This is the input. This is the positive half of the cycle. This is the negative half of the cycle, right? I can see for the positive half of the cycle, this type will become positive. This P type of this type will become positive and N type will become negative, or we can say this diode will be in on state for positive half of the cycle, right? For positive half, right? For positive half, this diode will be in the on state. And this diode will be in on state for the negative half of the cycle, right? For the negative half of the cycle, this end will be negative and this end will be positive. So this will be in on state for negative half of the cycle, right? For negative half. For negative half of the cycle, right? Right? Or we can say D1 will conduct for the first half or the positive half, and D2 will conduct for the negative half of the cycle, right? In both the cases, the output will be equal to input, right? Now this is the input and this will be the output. So for positive half of the cycle, this will conduct, right? Right. So this will conduct for the positive half of the cycle, right? And negative half of the cycle, this will again conduct, right? It means that it means that we can see that for both the cycles actually full wave rectifier conducts, right? So this will be the output for the full wave rectifier, right? Full wave rectifier. So it's once again a pulsating DC, right? Output is once again a pulsating DC, pulsating DC. But if we look at the time period, right? If the time period here is T, but here the time period is T by 2, right? So it means after half of the time period of the input cycle, the output completes its cycle, right? Or we can say if the frequency of the input is F, then the frequency of output is 2F, right? So this is the very important point with respect to the full wave rectifier. So output frequency is equal to 2 times that of input frequency, right? Or we can say frequency of output is equal to 2 times frequency of input, right? In case of full wave rectifier. So this is in case of full wave rectifier, right? Now let's talk about the different applications. This rectifier was one of the applications of the P injection diode, right? Now let's talk about the different applications of the what we call as P injection diode, right? So one of the important applications of P injection diode is the LED diode, right? That's the light emitting diode, right? It's a P injection diode, right? So we know that we use LEDs in our daily lives, right? We have LED bulbs, we have we use LEDs in remotes, we use LEDs in different sensors as well, right? So LEDs has got the broad applications in our daily lives, right? You must have heard about the LED TVs, right? LED displays, right? All these things are actually the applications of these semiconductor devices, right? P injection diodes. So how actually the LED works, right? LED works in actually in a forward biased condition, right? In the forward biased condition. When the LED is forward biased, then the electrons move from the N side to the P side and holes move from P side to the N side, right? So what happens is that at the junction of the boundary, their recombination of the whole electron pair takes place. And once these whole electron pairs recombine, right, there is the release of energy in the form of radiation, right, equal to the energy equal to or slightly less than the band gap of the uh, two band gap of the two sides. One is the valence band, another is the conduction band, because on forward biasing the conduction takes place, right? So there occurs or we can say the electron moves from valence band to the conduction band, right? So once the electron moves from the valence band to the conduction band, right? So recombination of these electron hole pair takes place, which leads to the emission of the radiation, right? And because of the forward biasing condition, and that radiation is actually used for the different purposes in case of LEDs, right? So if the forward current is increased, the intensity of light emitted is right. If the when the forward current of the diode is small, the intensity is less, and when the forward current is increased, the intensity will increase, right? And it will eventually reach its maximum, right? So every diode has its maximum limiting value because of the formation of the p-n junction diode, or the we can say depletion region, right? So further increase in the forward current will not result in what we call as increase in the intensity, right? So it actually results in a decrease of the intensity of light, right? So LEDs are biased in such a way so that there's a effective output of the intensity, right? Or we can say the intensity of the LEDs are maximized, right? So this is how the LEDs actually work. They're actually the forward biased p injection diodes, right? Where the recombination of the electron hole pair takes place, and because of the recombination, the radiations are emitted, right? The radiations are emitted, and these radiations are actually used for the different purposes, right? Different purposes in our daily lives. Now, the advantages of LEDs are that their operational voltage is very less, right? And they consume very less power, right? That's the reason we use LED bulbs and all, right? Because of their low operational voltage and their low power consumption, right? And the action of the LEDs is very fast, right? There is no delay in the action, right? Or we can say the there is no warm up type for the LEDs, right? And we can actually use these LEDs to get the monochromatic lights, right? Nearly the monochromatic lights using the LEDs, right? And one more important property of these LEDs is their durability, right? They have very long durability, or we can say they have the long life, right? So these are some of the major advantages of these LEDs, right? Which is a PN junction diode in a forward biased condition, right? So these are the great advantages of LEDs, right? So another application of the PN junction diode is the photodiode, right? It's the photodiode. So what we do in case of photodiode is that we incident a light energy of let's suppose energy equal to h nu, right? Light energy of equal to h nu on this photodiode, right? Now what happens is that the electrons in the valence band, right, absorb this energy, right, and they jump from the valence band to the conduction band, right? And due to that absorption of current, or we can say due to that absorption of the radiation, right? Uh, the current is established in the circuit because the electrons jump from the valence band to the conduction band, right? In the reverse bias condition, right? So actually, photodiode is used in the reverse bias condition. There's a reverse biasing in this diode, right? And once the intensity of the light is increased, the reverse bias current actually increase for different intensities, right? Because of the more absorption of radiation by the valence band electrons, and these electrons make a transition from the valence band to the conduction band, leading to the increase in the reverse current, right? So on increasing the intensity, the photocurrent goes on increasing, right? Or we can say photodiode is actually used to detect the intensity of light, right? So more the intensity of light, it will show more current flowing through it or more deflection through it, right? So actually photodiode can be used to detect the intensity of a given light, right? So you can see there's a plot between the reverse bias current and the intensity. You can see for I1 intensity, this is the reverse saturation current. This is the reverse saturation current for the I2 intensity. And this is the reverse saturation current for the I3 intensity. The reverse saturation current will be more for the photodiode whose intensity, where the intensity of the radiation is maximum, right? So here I3 should be greater than I2, it should be greater than I1 because of the greater reverse saturation current in case of uh, third photodiode, right? So this is how the intensity or the current depends on the intensity of the given radiation, and we can detect the intensity of radiation using the photodiode, right? Now, one of the important diodes, right, or the applications of the PN junction diode, that's the Zener diode, right? It's a very important application or very important diode, right? That's the Zener, right? Now, Zener is also a PN junction diode, right? Which works in the reverse condition, or we can say it works in the reverse biasing condition, right? And we can say it works in the breakdown region, right? It actually works in the reverse breakdown voltage region, right? So there are actually two types of breakdowns, right? One breakdown is what we call as avalanche breakdown, right? Another we call as Zener breakdown, right? So avalanche breakdown is because it occurs in a p-n junction diode having low doping, right? So breakdown voltage is very high. So depletion layer width will also be more, right? So the current will be because of the minority carriers, right? So when the minority carriers, charge carriers cross the depletion regions, right? They gain kinetic energy, right? Once the kinetic energy is gained by the minority carriers, so they collide with the atoms, right? Or they break the bonds of the atoms with other atoms, right? And this breakdown of the bonds leads to the formation of or a formation of other charge carriers, right? And eventually what happens is that the number of charge carriers increase because of this breaking or the collisions of these charge carriers with other atoms, right? So it ultimately increases the current, or we can say it breaks this diode, right? And this condition we call as the breakdown condition, and breakdown of this type we call as avalanche breakdown, right? And the damage done to the diet is actually a permanent damage, right? What we call as the breakdown, avalanche breakdown, right? Another breakdown is what we call as Zener breakdown, right? Zener breakdown is actually occurs in a heavily doped p-n junction diet, right? Breakdown voltage is very small, right? Depletion region is very thin. We know that for reverse bias condition, in case of avalanche breakdown, the depletion region is very high, right? Or we can say breakdown voltage is very high. But once the heavily towed p-n junction diode is formed, the depletion region actually becomes thin, or we can say breakdown voltage is very small, right? So when we apply the when we apply the reverse biasing, then the charge carriers increase, and there is once again the breaking of the covalent bonds, right, due to the electric field, right? Hence, we can say the damage is not permanent because it's a very small breakdown voltage, and the breaking of the bonds is because of the electric field, right? Not because of the collisions, right? It's because of the electric field, and this type of breakdown we call as Zener breakdown, right? So Zener breakdown has the very important application, right? It has the very important application because we know that Zener diode conducts only at the breakdown voltage, right? Once the breakdown voltage is established, then the Zener diode becomes in the on state, right? It becomes in the on state, or we can say it becomes in the working state, right? So Zener diode only and only works in the breakdown region, right? Or we can say, and we know that there is a specific or fixed breakdown voltage for every Zener diode, or we can say the breakdown voltage is fixed for the Zener diode, or we can say the output voltage of the Zener diode will be fixed in the reverse bias condition. So that's the reason we use the Zener diode as a voltage regulator in case of circuits, right? uh, the voltage across the Zener diode is always a constant in the on state, right? Here you can see this is the symbol of Zener diode, right? This is the symbol of the Zener diode. It's in the reverse bias condition, right? PZ we call as the Zener breakdown, right? Zener, breakdown voltage of the Zener diode, and IZ is the current flowing through the Zener, right? Zener diode. So this potential or this Zener breakdown will be the constant here, right? And this, because of the fixed nature of the Zener diode or working of this Zener diode, it actually works as the voltage regulator, right? So any resistor, any load, any capacitor, or any inductor connected to this Zener diode directly will actually have the constant voltage, right, equal to the voltage or equal to the breakdown voltage of the Zener diode. So that's the reason we say that Zener diode is used as the voltage regulator, right? It's used as the voltage regulator. It's used as the voltage regulator. So it means that whatever the voltage will be across the zener, if Vz is across the zener, then same voltage will be across this loop, right? The same voltage will be across this loop, right? Let's suppose IS is the current flowing through this zener, right? IS is the current flowing through this zener. Now this IS current will be distributed into two circuits. One will be across the zener diode, and another part of this current will be across the load resistor, right? So the total current has to be constant. Is is the source current, right? And Iz will be the current flowing through the zener diode, and IL will be the current flowing through the load resistor, right? But we know that zener here is a voltage regulator. Whatever be the voltage across the zener, same will be the voltage across the load resistor, right? Load resistor, right? So the VZ has to be equal to IL into RL, right? IL into RL, or that we can call it as VL, right? So this is how actually the zener works in the breakdown region or reverse bias condition, and it helps in regulating the voltage across any load connected directly to the zener diode, right? So it's one of the important application of the PN junction diode, right? That's the zener diode, and it's used to regulate the voltage across any electrical element or any electrical circuit because of the nature of the zener diode that it only works in the breakdown region. That's what we call as reverse breakdown voltage, right? So that's it with respect to the applications of the semiconductor devices, right? We'll be discussing some of the problems, right, related to it in the next lecture. We'll stop here. See you tomorrow, right?